Hello, this is Alistair Plotnick, and this is the magnetic field of a bar magnet lab. So first, just the introduction and purpose is to determine the behavior of a magnet at different positions relative to a bar magnet, create a computational model of the magnetic field produced by the dipole, both on and off axis, and visualize the magnetic field produced by the bar magnet. So first, the basic models used is the Savart law, the distance dependence equations for a magnetic field, the equation for the B field of a bar, and that the natural log of the bar equals natural log of K plus the natural log of the bar, and and the right-hand rule too. So here's a quick preview of our results, n equaled negative 3.18 meters, and the magnetic dipole 6.245 joules per Tesla. So first, the experimental procedure. The meter stick is set up to be orthogonal with the magnetic north along the east-west axis. Readings taken from the bar magnet using the magnometer on the Firefox app on my phone. Location of the magnetometer in phone were estimated. Phone was moved to a different distance to obtain different Vx values and measured on an axis at 45-degree angle. Components were recorded and linearized on an Excel spreadsheet. So first, the assumptions. As the magnometer moves closer to the magnet, the exponent of the magnetic field increases, and when the magnometer is far away from the magnet, it measures a near zero magnetic field in the x direction. So first, here is just a screenshot of the on-axis data, and you can see here how as the distance increases, it goes down, falls off, and here is the off-axis data as well. So here's the calculations. The distance dependence equation from linearization on the on-axis data, n equals negative 3.1828 meters. The Savart law from the magnetic moment, Bx equals negative 13.5651. And here I assume, excuse me, R was 1 meter, ln was negative 13.5651, and K equals e to the negative 13.5651, which equaled 1.285 e to the negative 6. And then here kr to the n equaled mu naught over 4 pi times 2 mu over r cubed, and here the magnetic dipole moment was 6.425 joules per Tesla. Here are the details of the coding for the glow script, and those will be linked in the description, or the code will be linked in the description of the video. So here, just going through the starter code and filling in the different vectors and setting up modeling what happened in the experiment. Here's the computational readout. So Bxs1, 8.224 e to the negative 5 on the x-axis. Same with Bxs2, and then Bperp was negative 4.112 e to the negative 5 on the x-axis, as well as Bperp2 and 3 and 4. D was 0.25801, and B at a 45-degree angle was 8.533 e to the negative 5, 5.56 e to the negative 5, and 0 in the z direction. So what if you hadn't oriented your experiment to compensate for the magnetic north and had instead laid out your meter stick at some intermediate angle with respect to the Earth's magnetic field? How would your results have changed? So taking the magnetic north into account sets an initial x component of the magnetic field to 0 Tesla, and only magnetic field of the magnet would be considered in our experiment. The Earth's magnetic field would interfere, otherwise the value in the x direction would not begin at 0 Tesla. And then what if your sticks, you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? The value of the magnetic field would be greater than the magnetic field from the experiment, but this does not necessarily mean it would have doubled, because there are other factors as well to consider. It's not just a 1-to-1 ratio. So, conclusions. The possible sources of error here could have been the magnometer, and the locations had been miscalculated, as well as just holding my phone in the app itself, how steady and accurate it was, with technological and human errors as well, and me doing the computations as well in the Excel spreadsheet. So the computational model was able to use the calculated values to accurately create a magnetic field at 45-degree angles of an axis of the magnet. And that is it. Thank you.